All right, AGS1. We're here to talk about Mod 2 closure notes. So these are the big takeaways from Mod 2 to get studied up for that quiz. One of the first things we started talking about was this word domain. Like, you might get asked, what is the domain of this problem? Remember, domains are everything that you can put into a function, or the inputs. Sometimes it's, time. Sometimes you're counting boxes of library books. Like, those are all domains. They're the X's that go into the function. There's two different types of domains. There's discrete and there's continuous. Discrete is usually the result of counting, and it's usually whole numbers, like 1, 2, 3, 4, 5. They're not connected, which means that there's no numbers in between. Like, if the inputs for the problem are 1, 2, 3, 4, 5, and not like 1.5 or 1.75, that means they're discrete. There's breaks between the numbers. We called those natural counting numbers just natural numbers, or this fancy n. An example of that would be like the number of students in a certain class. Because you could have 10 students or 20 students or something like that, but you wouldn't want to check like the 10.5th student because there's no numbers in between. Continuous means that there are no breaks, that it's like one smooth line. There are actually numbers in between other numbers. This is sometimes the result of measuring, like time is a big one, where, you could have an input of 1 hour, 2 hour, 3 hour, like those whole natural numbers, but you could also check 1.5 hours or 1.2 hours or 1.007 hours. So, example, let's see, 100-meter dash race times. Now, in Mod 1, we talked a lot about arithmetic sequences and geometric sequences, which we're still kind of talking about arithmetic, but now we're kind of moving away from that word into function land, where we just call that a linear relationship. The big thing about an arithmetic and linear equation, arithmetic sequence and linear equation, is they still have a common difference. They're still being go up or down, like a plus or minus same number each time between terms. You can start to think of this common difference as like the slope of the equation, and we have some ways to find slope. Oh, hey, haven't we done some slope equations? Just in case, our slope equation is y2 minus y1 over x2 minus x1. Linear equations are a straight line on a graph. And there's two different ways that we've been focusing on the equations. We've done a slope-intercept equation, which looks like this. Y equals mx plus b. Remember, this is your slope or common difference, if you want to think of it that way. And this guy is your y-intercept, or the zero term, is what we called them back when they were arithmetic sequences. The more recent way we've been forming equations of linear equations is point-slope form, which is y equals mx minus x1 plus y1. Please remember that this x1, y1 is any coordinate that's on the line. It doesn't have to be the zero term. It can or the first term. It could literally be any term. Now, you could always take this guy and use some algebra to turn it into this guy if you want. But just know that this is the form of point slope, and this is the form of slope intercept. Geometric sequences have turned into exponential functions in function land. They still have a common ratio, which means that it's a number that's being multiplied by each time. Remember that a lot of percentage problems. Those are the exponentials, like something that's going up by 20%, or like a pool that's draining and it's losing 15% every hour, something like that. In general, on a curve, on a graph, they look like a curve, but I don't want to just say any curve. Like if I draw something like this is not an exponential function, even though it has lots of curves. It's a specific curve. I like to think of it as a Superman taking off curve. So Superman starts out pretty low to the runway, but then once he crosses the y-axis, there's a pretty, like, high fly up into the sky type curve. The last thing I want to touch on is that we've been looking at 3 different versions of relationships or functions, whatever you want to call them. We've looked at tables, we've looked at graphs, and we've looked at equations. Now, you guys should be able to move in between these pretty easily. Like if we give you a table, let's say, you could turn that into a graph by plotting the points from the table, because remember, a table is just coordinates. Likewise, you could also take a graph, and if you know the actual coordinates, you could turn them back into a table. You might want to do that, like, if they give you a graph, but you want to look to see, like, how it's changing, like if there's a common difference or a common ratio, I would put it back into a table to, like, be able to spot the common difference or common ratio. Or maybe there's neither. There's not a common difference or common ratio. That does happen. Given an equation, you could turn it into a table. The way you would do this is just pick some x coordinates, throw them into the equation, and see what y coordinates come out of them. So you could build a table up for sure. Equation into graph. Have we done that much? Yeah, I guess with linear equations, we've done this right here, where you get like a y equals mx plus b, and you know the y-intercept, and you plot that, and then you use your little slope triangles, like, you know, let's say you know it crosses right here at the y-intercept, and then it goes up this many and over this many, so then here's the next point, and then you can start to build a line out of it. So we've done a little bit of that. I think mostly with linear. I don't think we've done, like, take a geometric equation and turn it into the graph. Not yet. It's probably coming. Now, let's think. Table into an equation. Yeah, you can we've totally done lots of this, that you guys can decide whether or not it's exponential or linear and try to build up an equation from it. Let's see. Equation to graph we've done. Graph into an equation. If it's linear, yes. So I'm going to say both of these are mostly on the linear tip. I don't think we've done much of exponential in that direction. But yeah, those are the skills you guys should have. All right, good luck on the quiz.